the cool thing with systems of differential equations is that you can actually draw what the solutions look like. And this is what's called a phase portrait, kind of like a picture. So solve x prime equals ax and draw the phase portrait where A is the matrix 1, 3, 3, 1. And remember, in order to do that, we need to find the eigenvalues and eigenvectors. But this, if you want, you can see in the notes. So eigenvalues and then vectors. I want to go right down to business. So what you find is that the eigenvectors are -2 with eigenvector, sorry, the eigenvalues are -2 with eigenvector 1, -1, and lambda equals 4 with eigenvector 1. And then remember, how do we build the solution? So step 4, solution. Remember, it is x of t equals constant e to the first eigenvalue, t times eigenvector, and then plus c2 e to the second eigenvalue, t times 1, times the second eigenvector. Okay, and how do you draw the solution with a phase portrait? So this is done in stages. 5. Phase portrait. It's literally like a profile picture. So first of all, it happens on the plane. So you have your two axes. And you see the eigenvectors, they're becoming your new axes. So first, you draw the eigenvector 1, -1, or more precisely, the line spanned by 1, -1, or the line with direction 1, -1, and then you draw the other axis, 1, 1. Because essentially the idea is on the axis 1, -1, you only have c1 e to the -2t times that. And on the axis 1, 1, you only have c2 e to the 4t times 1. Then on each axis, you want to draw some arrows depending on whether solutions go to 0 or away from 0. So if you look carefully, on the axis 1, -1, this e to the -2t term, it goes to 0. So this thing goes to 0, and in particular, the solutions, they go towards the origin. That's why you're drawing arrows going towards the origin. On the other axis, e to the -4t 1, 1, this e to the 4t blows up to infinity. And in particular, solutions on this axis move away from the origin. And that's why you draw arrows going away from the origin. So let me recap. On 1, -1, solutions go towards 0, so you draw arrows towards 0. On 1, 1, solutions go away from 0, so you draw arrows away from 0. Last but not least, all you have to do is connect the dots. So think of this as a velocity field or like wind, and you just have to follow the wind. So if you start from any point, because of the yellow axis, you move down, and because of the blue axis, you move up. So that's one thing, and that's another thing here. And then also here. And then also here. And again, just draw a couple of solutions until you get an idea of what's going on. And also here, solutions move this way. And finally, solutions move this way. And again, what are you drawing? Simply sample solutions. So you're drawing curves with solutions x1 of t and x2 of t. And if you want, here's a slightly more organized picture. See, once again, you can see the two axes, 1 minus 1 with solutions going towards 0, 1, 1 with solutions moving away from 0, and then sample curves of the solutions. All right, so now let's do another example of a phase portrait. So let's do the same, but with x prime equals ax, where a is 7 minus 3, 10 minus 4. And if you watched the previous recording, then you may notice it's the same system as before. And in fact, we found a solution x of t is c1 e to the t times 1, 2 plus c2 e to the 2t times 3, 5. And once again, we do the same thing. So we have our xy axis, and then you draw the vector 1, 2. So 1 right, 2 up. So this axis, that would be 1, 2. And then the axis 3, 5, which has slope 5/3, so a bit flatter. And by the way, it's okay to exaggerate this a little bit. We will not measure a ruler, don't worry. 3, 5. Yeah. And then what is going on? So once again, you look at each exponential term. So on the axis 1, 2, we have e to the t, which blows up to infinity. So solutions move away from the origin. And on the axis 3, 5, we also have e to the 2t, which moves away from the origin. So those arrows also go away from the origin. And the question is, what about in between? So here we can just really follow the arrows, but notice e to the 2t is much bigger than e to the t. So maybe let me write that down. So note, again, e to the 2t is much bigger than e to the t. That's how you write much bigger. So eventually, the solutions will just look like the second part, c2 e to the 2t. So x of t. In other words, if t is large, x of t looks like c2 e to the 2t 3, 5, which really is a constant times 3, 5, so it becomes parallel to 3, 5. So in other words, how do you draw the solutions here? Well, it kind of starts like more or less at 0, 0, because as t goes to minus infinity, it's 0, 0. And then it just eventually just becomes parallel to 3, 5. So it might curve at first, but then it looks like 3, 5. Also here, it might curve at first, but then looks parallel to 3, 5. Also here, and also here. And same thing in this case, it might curve, but eventually becomes parallel to the blue line. And here as well. And also similarly here. Maybe like this. And we also did the other case. So once again, this is roughly what it looks like. I want to show you a nicer picture once again. Once again, here's a nicer picture. I drew the two eigenvectors and their axes. And again, because this e to the t, e to the 2t goes away from the origin, you draw the axes going away from the origin, and then you draw sample solutions where they eventually become parallel to 3, 5. So once again, 3 steps: axes, orientation, solution. And one more thing, if you had e to the minus t and e to the minus 2t, it's the same thing, but the arrows would turn the other way.